Hello, you guys. So I had a really fun morning. I got to school for the late start, dropped my kids off at Cardinal Club, walked into my classroom, and immediately got a call from the elementary school that Zandy had cut his chin open on a scooter. It was scootering around the gym apparently, and then managed to. Here's the cat. Come on, kitty. Managed to fall off the scooter and slide across the gym on his chin only. Anyway, he ended up cutting it open and needing. We went to the urgent care and got it glued back together. So he is now happily sitting and enjoying his day off and making sure to be happy that he is missing his spelling test today. So everything is okay with him, but I'm at home. All right, let's see how fast I can do this. So 5.5, using a normal distribution to approximate a binomial distribution. Now, it seems like we wouldn't need a normal distribution because we know how to do binomials. We've got a calculator that can do it for us and so on. The reason why we use a normal distribution for binomial problems is because once n gets really high, it becomes, I don't know, tedious, ridiculous to do that many formulas. What should I call it? It is not practical, I guess. Like if I said somebody was doing a surgery on 10 patients, yeah, that's easy to do with a binomial formula. But if it turned out to be 150 patients or 2,000 patients, then you'd have to do all those formulas and add them together if you wanted something that was like fewer than 200 successes or whatever, and even your calculator can't handle that after a while. So, all right. If you look at this normal distribution here, n is 4, and you can see that when n is small, that it doesn't really look very normal. But then when n gets larger, and n gets larger, and n gets larger, it really turns into kind of a normal distribution because you have whatever your average is right in the middle. That's what's expected. And then so, like let's say we were talking about 50 surgeries. Then you would expect maybe, depending on the ratio of success, maybe 13 of them to go right, but sometimes 12 go right, sometimes 14, sometimes etc. And so it kind of planes off on either side. It's really unlikely that 21 surgeries would go right, but it's also really unlikely that only 5 surgeries would go right, and so on. So to do a normal distribution with a binomial, we have to test 2 things. The first thing you have to test is that n times p and n times q is greater than 5. P being your probability of success and Q being your probability of failure. And you also have to verify that it is binomial. So by that you want to probably specify n, p, and x to make sure that you know that it is binomial. Okay. All right, let's try this one. In a survey of adults in the United States, a certain percentage of them say that they have seen people literally walk in front of, looking for my stuff here, walk in front of a moving vehicle without looking. Apparently that was 34% was predicted that way. You randomly select 100 adults in the United States, ask them whether they've seen a person using a mobile device walk in front of a moving vehicle without looking. All right, can this be normal? So the first question is, do we have an n? Yes, n is 100. P, probability of success. Sadly, the probability of success right now is walking in front of a moving vehicle with a car. So your probability of failure would be 0.66, which is just 1 minus 0.34. So we have n, p, and q, so we know it's binomial. And then we have to check, does n times p, is that greater than or equal to 5? And is n times q greater than or equal to 5? So for that, I'm going to take, well, okay. So let's see if I've got my app on my calculator. I was not prepared to teach from home today. Okay. So this one, I mean, I really don't need a calculator, because if I take n times p, that's 100, times 0.34, which is 34, and that is definitely larger than 5. If I take n times q, that's 66%, which is also larger than 5, because that would be 66. However, something to note is that you really only have to test one of them. If you test the smaller one and it doesn't work, well, then that means that it's not going to work. And if you test the smaller one and it does work, then it is definitely going to work. So if you test the smaller one, you should be good. If, by the way, you can't use a normal distribution to approximate the binomial, then you just use a normal or a standard binomial. Shouldn't say normal anymore, right? Distribution. Now, the only problem with this is we have to do something called a correction for continuity. A correction for continuity fixes the fact that binomials are discrete, not continuous. Continuous. All right. So, for example, a correction for continuity to convert the following binomial intervals to a normal distribution interval. All right. So let's say that you've got a whole bunch of stuff here, and it's kind of making these. Remember, it looks kind of like a bar graph going up, because these are discrete, not continuous. So it's not technically a bell curve. It's something that looks about like a bell curve, like this. Now, if you think about 270, I know that this isn't enough bars, but let's say that this one is 270 and this one is 310. If I use my normal distribution, it would come off right here in the middle of that bar, and right here in the middle of that bar. And we want that whole bar to be counted, so we actually have to scoot over the number that we're using in x minus mu over sigma just a little bit to account for this other half of the bar. So imagine like this half of the bar is missing. And if I'm going too fast for you right now, remember you can always pause and go back. So this half of the bar is missing, this half of the bar is missing, and it says inclusive, as if we want 270 and we want 310. So to change this, instead of using 270 and 310 in the x minus mu over sigma, we're going to use 269.5 and 310.5, just going that little extra half a bar to include the entire bar when we're talking about it. Okay, let's try this one. At least 158 successes. Okay, so here's my distribution again. Very fancy looking. Doesn't have to be perfect, clearly. I mean, look what we got here. Okay, so let's say that this one is 158. We want at least 158 successes, which means we want here and over, we want that whole bar to be counted. But right now,